All right, so the goal is to graph 1 over f of x, and you guys in the previous example had done some exploration about what does 1 over f of x do if f of x does some stuff. And so I'll go ahead and start with, what will we start with? We'll start with the x-intercepts of that blue graph over there. If you are looking at this point right here, how much is y? 0. And so I know that f of 2 is 0, which means if I'm thinking about the graph of this, 1 over f of 2, I'm really trying to do 1 over 0. And 1 over 0 is very bad, but generally having zeros in the bottom creates what on the graph? Is a vertical asymptote. Zeros in the bottom of a function create vertical asymptotes on the graph. And so what we've just figured out is that there's actually a vertical asymptote at 2. I'm thinking of the graph of y equals 1 over x, 1 over f of x. Where's the other vertical asymptote? The other place where the y is 0 is at 0, 0. So again, I'll draw it in purple, but it's just the y-axis. So I've got 2 vertical asymptotes. Is the second what? Is this? It could make that shape. So Topher right now is doing something like this, right? Isn't that one of the possibilities? Like, there's not that many possibilities. It could be that. It could be the other way. It could be both of those, and it could be both of these. It's one of those 4 things. We just have to figure out what it is. Okay, so we will decide, but let me first think about, well, actually, let's decide right now. In between 0 and 2 corresponds to in between 0 and 2. What kind of y values do you have over here the whole time? They're all positive numbers, right? All of these y values are positive. When I do 1 over something positive, what kind of a number do we get? Positive. So of the different options, you know, we had that one, and we had that one, and we had up here, and we had down here. You need to pick the one that's always positive, the one that's all the way up there. So I feel pretty good drawing something like that. And I could say even more. I could tell you where that bottom point is. This point right here means f of 1 is 1. I don't have the picture in front of me, but roughly f of 1 is 1. So if I put in this function, I throw 1 into that function, I'm really doing 1 over 1, which is 1. So this point right here, I think, is also 1, 1-ish. Okay, next thing I'm going to think about is this part of the puzzle here. If I run to the right forever, I have to go down forever. So the right forever, down forever, that is to minus infinity. If I try putting minus infinity in for the bottom, because that's what the y values are doing, 1 over negative infinity, it gets close to a really nice number. 1 over minus infinity, what does it get close to? It gets close to 0. 1 over something really enormous goes to 0. So if I run to the right, I need to get closer and closer to 0. So on the graph of this function, it's either going that way or this way, getting very, very close to 0. If I run to the left, what's happening to the y values originally? The y values go to negative infinity. Again, I'm trying to do 1 over negative infinity, and it still approaches 0. So it's either this or this. And so then I'll go ahead and continue. I mean, like, this guy has to approach the vertical asymptote, either down there or up there. The same thing on this side. And again, we're just kind of choose your own adventure. We have to pick, it's not both. You got to pick either the top one or the bottom one. And so to make this choice, looking out here, is like looking out here. What kind of y values do you have out here? They're all negative y values. And if I do 1 over a negative number, it's still negative. So which of those two green branches is the correct one? The one that's negative. Now we'll take a look at the far right. Those x values are like these x values. What kind of y's do you get out here? All negative. So when I do 1 over a negative, I get negative. And again, we erase the top branch because it's always negative. So something like that. So graphing 1 over a function is really quite complicated, and it's something that we have no practice with until now. You are starting to practice with the graphs of 1 over functions. And so there's kind of crazy stuff that happens, but with a little bit of practice, it becomes less crazy and more orderly. Are there any questions on that one? Okay, then can you guys open to page 9 in the packet? While you're doing that, a couple of things. First, I'm up to 200 views on YouTube, so the sky is the limit. You know, like I guess I didn't really have a sense, but yesterday, you know, we had all that weather, right? I'll zoom in a little bit here. And in my 107 class, which happens at 1 in the afternoon, I was missing probably about 40% of the class. Just I maybe couldn't make it or had to leave early because the weather was coming and it was kind of bad. And so to have 6 views in a class with 20 students, that was my class from Wednesday. Like that's, I don't know, makes me feel kind of good that like I'm expecting this is some of the people or maybe all the people that missed class, you know, were able to take a look at this. So, so I think that's kind of cool. And the other thing, I'm still trying to catch Allie and I'm not close yet, but we'll work on it. Her score again was it 15,000 and change? 15.5? Yeah. Yeah, were you not here when we saw the, yeah, it's crazy. Okay, so today is a special day, March the 2nd. We begin our study of trigonometry, and I hope that you guys like it because it is going to occupy us for like the next 6 weeks. I mean, like this is a major, major component of the course. It is okay if you have no experience with these funny things called sine and cosine and tangent. I'm assuming you have no experience with them. If you've seen them before, great. But this is where we begin our study of trig. Project number 4 is officially due at this moment, so I'm hoping a bunch of them are in the folders. Remember, it's okay to turn the projects in up to a week late. There are penalties depending on when you turn them in if it's late, but you know, better late than never. Oh, project 5. I guess I owe you that one right now, right? Yeah, I'll go get that at some point today. All right, so project 5 will be assigned, and then it's due on March the 9th. Any questions on the calendar? Okay, if I forget, can somebody remind me at the end of class? I owe you the projects. Okay, number 1, Jacob.
Let's explain today as we begin our study of a super important area of mathematics known as trigonometry. Start with a quick review of some basics about it.
Stephen?
Some of the measures of triangles.
Okay, how many degrees do you get when you add up all 3 angles? I heard a 360, I heard a 180. Yeah, for a triangle it's 180. For a quadrilateral it's 360. And can you guys just real quick sketch a 90-degree angle, a 180-degree angle, and a 360-degree angle? Okay, so I have not defined what a degree is, but I feel like you guys have seen it before. A degree is just a way to measure an angle. Would you say 1 degree is big or small? 1 degree, generally speaking, is quite small. I would have an awful hard time even showing you a 1 degree angle because the lines here are so thick relative to like a 1 degree angle. Imagine taking this 90-degree angle and cutting it into 90 small pieces. I would have a hard time showing you even what one of those pieces is because it's so small. Generally 90-degree angles, we have this little symbol, kind of make it look like a square, and that's how we indicate it's a 90-degree angle. 180 degrees is like like go the other way. So if you were walking to the right and I said rotate 180 degrees, you would then be facing to the left. And then a 360-degree angle, how do you draw it? Well, I don't know that, I guess. I mean, like there's no, like the start and the end are exactly the same. So rotating 360 degrees will look exactly the same when you're done as when you started. Anyway, I guess all we're saying is that 360 degrees is 1 revolution. So far, so good? Okay, and we'll go back to Stephen for the last part. Okay, so theta is a Greek letter. It generally is used for angles, and your calculator does have a button. We have been using this button for x, but if you look carefully, you will find some other stuff on that button, including one of these things, theta. Okay, there might even be a theta somewhere else. Is there a green one towards the bottom? Is that above the 3? Is that a theta down there? Yeah. So your calculator has some thetas. Okay, next page, number 2, Ali.
Two triangles are similar if the corresponding angles are blank and if the corresponding sides.
Okay, do you guys remember from maybe geometry what it means to have two triangles that are similar? And I will tell you that the picture of the two triangles down here, those are similar triangles. What do you think is true about the angles? Yeah, angles are exactly the same. So they both have a right angle. They both have this thing called theta that's just the same. And then the third angles are the same as well. So corresponding angles are equal. And then something is true about the corresponding sides. Are they also equal? No. Yeah, there's a ratio thing, and somebody mentioned the word proportion. For example, there is a famous right triangle whose sides are 3 and 4 and 5. And if I were to tell you, for example, that this side over here is 6, the 6 is what the 3 used to be, and the 3 got doubled. Well, it turns out in similar triangles, every side gets doubled in this case. So the bottom would be an 8, and the hypotenuse would be a 10. So with similar triangles, the angles are equal, and the corresponding sides are proportional is the fancy word, but if you don't know what that word means, it doesn't really help you. So we will translate in saying, corresponding sides are in the same ratio. In the example we just made up, the ratio is a 2 to 1 or 1 to 2. Okay, number 3, Chris.
Let's look at a right triangle from the vantage point of an angle, theta. The two legs can be called the adjacent side, the opposite side, and the long side is the hypotenuse. Let's label the sides of the smaller triangle.
Okay, so we've got the long side in the triangle is the hypotenuse. That's this one over here. The hypotenuse is always opposite which angle? It's really far away from the right angle. The hypotenuse of a right triangle is the one that's the one directly opposite from the right angle. It's also the longest one. And then we have these other two words. We have adjacent side and we have opposite side. Now, adjacent generally means like next to or nearby, and opposite generally means kind of far away. Which one is which depends on your perspective. We are taking the perspective of sitting at this angle theta. So imagine yourself right there. And you have these two other sides. Which one would you say is the opposite one? Would you say the vertical or the horizontal is the opposite? Yeah, the opposite is the vertical one, so that's the opposite. and the horizontal one is adjacent because it's right next to, it's part of the angle theta. Does that make sense? If I were to talk about this angle, capital A, which one is the opposite side for capital A? It's the one on the bottom. Opposite to A is down here. So opposite and adjacent very much depend on which angle you are thinking about, okay? Hypotenuse is always that same one, no problems there. Okay, number 4, Kelsey. All right, so I guess I already gave this away, but these two triangles are similar. And so the angles are copies of each other and the sides are in the same ratio throughout. Topher. Okay, let's pause there. Let me put these numbers back. You don't need them, but just putting them up here. For example, take a look at this ratio, opposite over hypotenuse. For the small triangle, with respect to that angle theta, which one is the opposite side? This is the 3. And which one is the hypotenuse? This is the 5. So for the small triangle, this ratio is 3 over 5. Yes? You don't need to write that. For the big triangle, think about the same opposite and hypotenuse. Again, from the perspective of this theta, which one is the opposite? Is the 6. Which one is the hypotenuse? 10. So for this triangle, that ratio is 6 over 10. But what is 6 over 10 really? It's really 3 over 5. And the point here then is that if I'm thinking about opposite over hypotenuse, it makes no difference how big or small the triangle that you're talking about is. If we have two triangles that are similar, because they have the same angle theta, then the ratio will be equal as long as you reduce at the end. So, okay, so that's fine. And then Topher, you can keep going. Okay, so 3 new functions that we will be revisiting many, many times over the next 2 months: sine, cosine, and tangent. What's the input of each of these functions? Is theta. What you put in is some angle. You could say, oh, the input is this angle right here. That's theta. That's the input. And it turns out that opposite over hypotenuse is something we are calling the sine of that angle. What was the sine of theta in this case? Opposite was 3, hypotenuse was 5. This thing right here is the sine of theta. Sine of theta. You don't need parentheses, but I'll put them just to highlight it's not a multiplication, it's an of. Sine of theta. Yeah, so that's it. So then, you know, like that sine symbol is, you know, quite similar to like the square root symbol. You guys know what to do when you see some number inside of the square root. So square root of 9 means something to you, right? Sine of is just a function, right? Square root is some function. It takes in a number, it spits out a different number. Sine is another function. It takes in an angle and it spits out a ratio. Square root of 9 is 3. Sine of this particular angle in the picture is 3/5. Okay, let's try 6. Melissa. Okay, can you guys try it? So we're looking for sine theta, cosine theta, and tangent of theta. 3 ratios, the definitions are right up above. Check with your neighbors. Check with your neighbors out loud. Okay, any questions on the three ratios? 5/13, 12/13, and 5/12. Is that okay? So if you're looking at a picture of a right triangle, these three definitions, it's just a matter of grabbing the correct sides and putting them in the right order. Okay, we'll try 7. We'll go back to Steve. Okay, so let's try this. Our first application for why do we care about these three funny things, sine, cosine, and tangent. All right, so first it says the adjacent side is 10. So again, from the perspective of that 25, the adjacent is the nearby one, it's this bottom one. So the adjacent is 10. The difficulty here is that I can't do I don't know what the opposite side is, and I don't know what the hypotenuse is. But what I'd like to do is figure out how long they are. So let's think about this. Let's write down what the definition of tangent is. Tangent of theta, which is a 25-degree angle here. What over what is the definition of tangent? It's opposite over adjacent. Okay, the opposite I don't know. I'm just going to write OPP divided by the adjacent. The adjacent side is 10 in this case. All right, so first, I've made a slight change. I used to be calling it tangent of theta, and now I've actually named the degree measure of that theta, but that's okay. So tangent of 25 is the opposite over 10. Well, here's the deal. Tangent of 25 is some number. If I knew what the opposite and hypotenuse were, then I could just tell you what the number is at the moment. Well, I don't know what it is, but there are a lot of people that have come before us in centuries and have gone through very, very specific calculations, and they have already figured out what the tangent of 25 is to a high degree of accuracy. So the tangent of 25 is just some number. It's some opposite over adjacent. It's a ratio, but it makes little difference that it's this particular triangle with the 10 on the bottom. It could have anything on the bottom. Any triangle similar to this one would give you the same value for tangent of 25. And so tangent of 25 is now something that's look-upable. We can think of it like Googling, like it's something that it exists. We just have to figure out what it is. And so you can actually go on Google and ask it for tangent of 25. The calculator can also tell you what the tangent of 25 is. So let's look it up. First thing to do is make sure we are in the right mode. It's going to turn out that degrees are just one way to measure angles. So I said 90 degrees and you guys all had this image in your head. There's another way that we're going to think about angles, and this other way is coming up in 2 classes. It's called radians, and we're going to spend a lot of time thinking about what those things are. All of calculus is not done in degrees. It is done in this other way of measuring angles, just like you could do feet, or you could do meters, you could do degrees, or you could do radians. So it's going to be really important throughout the semester to be sure that your calculator is in the right mode. And what mode you should be in just depends on what you're working with. So hit the button that says mode. It's in the top row. And if you go to the third choice, you will see there's an option between radians and degrees. Whatever you are in now, make sure that you're in degrees by the end. So just scroll over, highlight that one, make sure it's solid, and then you can hit the clear button to get back to the home screen. Okay. Now I'm going to type in the tangent of 25 degrees, but not yet. I want to make sure that you understand that again, this is just like doing research. It's really just looking up something that's known. Suppose that I had a 45, well, in fact, why don't we suppose that we have the 45-degree thing that's down below. Take a look at this picture right here, lower left. This is a 45, 45, 90 triangle. When 2 angles are the same, the triangle has a special name. Starts with an I. Equilateral means all 3 angles are the same. Isosceles means 2 angles are the same. Okay, we don't really need that word. What we need is that if 2 angles are the same, do you know what other 2 things are the same? Is the 2 sides. So if you just kind of go opposite the 45s, you will land on 2 sides that have to be the same. And looking in the picture, it seems reasonable. So I don't know what this thing is, and I don't know what this thing is, but it makes sense to call them both x. They're both the same. If I wanted to find the tangent of 45 degrees, remember tangent is opposite over adjacent. for this 45-degree angle at the bottom. Which one is the opposite, the horizontal or the vertical? The vertical is the opposite. Adjacent is down here. So if I'm thinking of tangent of 45 degrees, it's opposite over adjacent. How much is the opposite in my picture? X. How much is the adjacent? X. What is the tangent of 45? It's 1. Doesn't matter how big or small that 45, 45, 90 right triangle is. The tangent of 45 will always be 1. These guys will always be exactly the same number. So that's the first thing I want to type in on my calculator just to see if it's doing things that I expect. Most of the numbers when you type in a tangent are going to be ugly. But tangent of 45 is a nice number. So if we've done this right, you type tangent, it automatically puts parentheses because it knows it's an of, tangent of 45 degrees, and it should say 1. And if we were to type in tangent of 25 degrees, which is the number that we're interested in, we'll get some other answer. Not 1, nothing nice, but there it is, except that's not right. Let's try again. Tangent of 25 is that. This means something. The opposite over the adjacent is 0.466. Think of it as a percentage. That's like 46%, right? The opposite over the adjacent is 46%. The opposite side is 46% of the adjacent side. Does that make sense? If you have a 25-degree angle, so I'm just thinking about this. 25 is not all that big. Is it believable that maybe this guy over here is like 45% as long as the one on the bottom? It stands. I mean, I don't know if it's, I can't tell, but I mean, it's reasonable. It's a lot shorter than the thing on the bottom. It turns out it's 46.6% of the thing on the bottom. And if you buy that, if I were to type in the tangent of 10, would this percentage get bigger or smaller? Yeah, that 10-degree angle is even shorter than the one that I've drawn here, so that vertical side gets even smaller. I can keep the bottom one the same, so tangent of 10 should be even less. And all right, so it's only 17% if you're at a 10-degree angle. So you can play this game and get this ratio, but again, it's just looking up stuff that's already known. So let's see if we can use that tangent of 25 degrees. Up here, we had this equation in blue. Tangent of 25 was opposite over 10. Tangent of 25 was 0.466. That's the opposite divided by 10. And then do what to both sides? Multiply by 10. So 10 times 0.466 equals the opposite side. Opposite side is around 4.66. Questions on that? Okay. So I said that was our first application of why we care about the tangent and sine and cosine. Is it okay? We were able to figure out what the opposite side is. Now that's not so exciting couched in the language of triangles, but suppose that it wasn't just triangles here, but rather you were a person standing over at this point, and this right here is the edge of some building that goes back this way, and you wanted to know how tall the building was. Well, generally it's not feasible to stand up on the top of a roof and get a really long tape measure that you can hold over the side of it, right? But do you believe that it's easy to measure how far you are from the building? It was 10 in this case. That's a whole lot easier than measuring the vertical distance of the building. Do you also believe that I could estimate like a 25-degree angle? Like if you're just standing there and you look up, I mean, all right, so it would be very crude to just stand there with like a protractor, but even with a protractor, I could estimate it's about 25 degrees. But engineers have very fancy and very simple tools that they use to find angles of elevation, they're called. So the point here is that you can oftentimes measure something that's quite difficult to measure, if not impossible to measure directly, using sine, cosine, or tangent. The 25-degree angle is easy to calculate with a tool. 10 is easy to calculate with a tool. The height of the building is hard to calculate with a tool, but really easy to calculate with sine, cosine, and tangent. All right. That's how we do what? Okay. Yeah. So certainly we could not measure the height of the rocket by somebody standing up there. It was a model rocket, right? Yeah. So we can't have somebody like standing up there with the tape measure. So we use a protractor and we measure something that's easy to measure, and we use sine, cosine, tangent. Thank you. Okay, 8. I think we're back to Todd. Okay, we'll go to Sam. Okay, so looking at the 45, 45, 90 triangle, we've already established that the two legs, the two short ones, are the same. Just to make them nice numbers, I'm going to call them 1. And then what theorem can you use to find the hypotenuse? The Pythagorean theorem, a squared plus b squared equals c squared. And if you do that, you will find the hypotenuse is the square root of 2. Great. 1 square root of 2 is a list of 3 numbers that I have memorized. If you memorize them, you can just label your triangle from scratch. Labeling the other triangle is a little bit more involved. I'm not going to go into the details, but see me if you want to see the details. But generally, across from the 30, we'll just call it a 1. We'll just set up some base number. Turns out the hypotenuse is exactly twice as long as that short side. Always twice as long as the short side. 60-degree angle is something that's always square root of 3 times the short side. Not clear, but Pythagorean theorem gives you square roots a lot of the time, right? I mean, a squared plus b squared equals c squared. And square root of 3 is between what two integers? Isn't it between 1 and 2? Like square root of 3 is about 1.7. Okay, so short is 1, medium is square root of 3, big is 2. And in my head, I have memorized 1, 2, square root of 3. And now that we have all this stuff, we can then fill in this chart right here. We're going to end up using these numbers a bunch. I'm just going to fill in like 2 of these, and then you guys can fill in the rest for practice later. But for example, the sine of 30 degrees. Remember, sine is opposite over hypotenuse. And so go look at one of our special triangles down at the bottom. Find the 30-degree angle, and write down the opposite, and write down the hypotenuse. What's the opposite for the 30-degree angle? It's 1. What's the hypotenuse for the 30-degree angle? 2. The sine of 30 is a half. And your calculator will confirm that if you ask it for the sine of 30. The only other one I'm going to ask us to do right now is the cosine of 45. So find the 45-degree angle, either of them. Cosine is adjacent over hypotenuse. What's the adjacent side for the 45? 1. What's the hypotenuse? Square root of 2. Now, radicals in the denominator send shivers up the spines of some mathematician. I'm quite okay. I can live with radicals in the bottom. Took a lot of years of therapy, but it's fine with me. So you can leave radicals in the bottom. You could put them upstairs if you prefer. Topher. We're going to talk about the unit circle, and you can use the values however you wish. Okay. My goal is just that we can come up with these numbers however we can. Great. Okay, number 9, I think we're back to Emily. Okay, so let's try this. So here's my building. Lovely. And we walk 100 feet away. So that's my 100 out there. And then we look up to the top of the building. And we should get a picture that is hopefully familiar to us. And it says the angle of inclination is 38 degrees. You guys know where to put the 38? Seems like there's two choices, but only one of them is right. Yeah, it's from the perspective of the person who's making this observation. And that person is, you know, the horizontal is straight ahead and the top of the building is 38 degrees up, and that angle is exactly what we call angle of inclination. Can you guys use some sine, cosine, or tangent to find the height of the building? So which trig function is the one to use here? Tangent. So we know tangent of 38 is the opposite side, which we want, divided by the adjacent side, which is 100. Instead of typing in tan 38 at this moment, I'm going to go ahead and multiply both sides by 100. Do you guys buy that? So the opposite side is 100 times the tan 38. And the nice thing about that is that then we avoid rounding error to the extent that we can avoid rounding error. So I'll just type in 100 tan 38 in one shot here. And so it turns out the building is about 78 feet tall. Questions on that? These numbers were made up. It's probably not 78 feet tall. No. One thing, this will look very strange. I'm going to change to radian mode. Don't you change to radian mode. But if I decide to type in exactly the same thing, it will give me exactly a different answer. But often, so we don't know what radian mode is, but somehow it dramatically changed the answer. This is not the right answer. But if I weren't, like, I probably wouldn't even know that that's not the right answer. Like, I'd be quite content to write 31 feet. So like, it's really, really easy to write the wrong answer if you don't think about what mode you're in. So I'll be saying this a bunch, but anytime you use any of these three buttons right here, sine, cosine, tangent, first go into the mode and make sure you are in the right spot. No, the only thing that the degree radian mode affects is those three buttons, sine, cosine, tan. Good question. Okay, 10, and we're back up to Tacitae. Okay, let's fill in the blank. Accidentally put degrees, thank you, Chris. Sine, cosine, tangent, right now the input is, well, the input is an angle. But what's the smallest angle that would make sense in our triangle? Like 1 degree, or, well, it could do even half a degree, right? But, you know, yeah, like greater than 0 is the only thing that makes sense. And what's the biggest angle you can fit in a triangle? Normally you could fit like a 179 and change, right? But this is a right triangle. Our definitions only apply to right triangles. So what's the biggest other angle? Is 90, and you can't even fit a 90 in there. So at the moment, our trig functions are only defined between 0 and 90. Now, if you're feeling particularly daring, you could go to your calculator and hit sine of 91, just to see what it does. Does it destroy itself? You like implode? No, it gives you a number. Okay, so there's something happening beyond 90 degrees. We don't have a way to get there yet, but we will very soon. But at the moment, only between 0 and 90. Okay, 11, Kate. Okay, so if you write down this made-up word, it may help you remember the definitions of sine, cosine, and tangent. We read that as Sohcahtoa, which is supposed to tell you that the sine is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over adjacent. Now, Sohcahtoa is only going to help you if you spell it correctly. So however, what's that? Yes. Somehow you need to know that sine is opposite over hypotenuse, etc. So if that word helps, then super. 12, Richard? Okay, we'll go to Chris. Go ahead. Okay, let's pause right there and take a look at the funny picture at the bottom. So this thing repeats, and so we call it periodic because it repeats. If you can tell me how long horizontally it takes to repeat, then you have found something we are calling the period. So in the picture that's printed, they have written the period is the distance from that top point all the way out here to this top point. So what's that horizontal distance? Looks like it's 6 because it started at 3 and ended at 9. So the period of this function is 6. How long does it take to repeat horizontally? Now there's no reason that you have to pick top points. You could pick, for example, bottom points. And do you guys see that that one starts at 4 and ends at 10? Also 6. You could pick, like this point right up here on the curvy part. It becomes difficult because then it's kind of hard to know exactly where the corresponding point is, but if we buy it, then 5 to 11 gives you the same 6. Okay, we'll go to Kyle, midline. Okay, so it would be uncomfortable having me cut this pattern in half because it is not symmetric on the top of the dotted line compared to the bottom, right? But it does have a middle in that there's a point that's exactly right in the middle of the highest point ever and the lowest point ever. And if the highest point ever is, what number is up here? 4, and the lowest point is -1, there's a middle between 4 and -1. What is the middle between 4 and -1? It's 1.5. And that's what we're going to call the midline, a line that goes right through the middle. And so for us, the midline, which is also called the axis in this example, is y equals 1.5. And there's an easy way to find it. You just do I can say that the midline is the maximum y plus the minimum y divided by 2. That's how you find a number halfway between two other numbers. You average them. Any questions about the midline? Okay, so the project that is assigned today is getting handed out right now. And just while I'm thinking of it, there's something else that's on your tables too. There's a challenging math competition exam thing that some GCC students participate in each semester. I have put examples of this competition on your table. So if everybody could grab one, there actually should be 2 things you should grab. One of them looks like this with a bunch of questions typed very close to each other. And the other thing should look like this. Everybody have 2 things? There's a front and a back, so you might have to look around to find the stuff we're talking about. So this competition for GCC is happening Wednesday coming up, and it's going to be in this room right after class from like noon until 1. If you have class at 1, then you leave at 12:50 or 12:30, whenever you want to leave, you just leave. Steve. Okay, so what can I tell you about this? What are you looking for? Oh, the project, right. Okay, so about this competition. First of all, there is no cost to you, so that's a good thing. Second of all, people that do, this is a nationwide competition open to students in 2-year colleges across the country. And the students who do really, really well on this exam actually win some prize money. So there's like scholarship type stuff happening, but you got to do really, really well on this exam to get that kind of money. Really, for me, the point of taking this exam is, number one, GCC gets ranked nationally depending on how our top scorers do, and our top scorers are defined to be the people with the 5 highest scores. But the good thing is we don't have to decide who those 5 people are going to be beforehand. It's not like we have to pick a team and say, this is our 5. We just get as many GCC students taking this test as possible and score everybody, and the top 5 are our team. So the more people take it, the better our chances are of getting a high top 5. The questions are all at the pre-calc level and lower. So in theory, you have seen most of the material that is on this exam. Certainly there will be some stuff with sine and cosine that we're just getting into that you won't have seen before, but that's okay. If you are interested in just taking a very challenging exam that will kind of stretch you, then I think it would be great to have a bunch of people from this class show up. If that wasn't motivation enough, if you show up, I will give you credit for doing a homework assignment or questions of the day, whatever will help you. I will pad your grade a little bit in that way if you are willing to take this test. The rules are on one of these sheets just so that you're prepared to, like you'll know what to expect if you decide to come. Yeah, that's good. Any questions on any of that? Stephen. Test is going to be Wednesday coming up right after class. And if you only want to spend half an hour on it, then leave after half an hour. You're not committed to like staying for an hour if you don't want to. You're allowed to use your graphing calculator. You don't need to show any work. So you can just like make pretty patterns with the choices if that's how you want to do it. Like it's fine. Yeah, I mean, I think it's nice to be challenged, and this exam will push you, and it will ask you to put together ideas that you've seen in ways that you haven't seen, which I think is a good thing. Yeah, Topher. There are answer sheets online. I can show you guys. So I don't have answer sheets that I printed. In fact, I've printed several different exams for this class. So if you just Google Matic, then I can show you where you'll find old exams. Matic Student Math League, and then past, what am I looking for? Competition questions. And right there you will find all the exams from like the last almost 10 years. It happens every semester. So, and then answer keys as well. Okay. So if you just type in Matic, you will find this. Any other questions about this? Okay. All right, last thing we were at was amplitude, Vance. All right, so amplitude is how far it is between the middle and the top. So how far is it between the midline and the top? It's 2.5. Everybody see it? Or from the middle, which was at 1.5, all the way up to 4. Equivalently, you could go from the middle down to the bottom. How far is that? 2.5. So it doesn't matter which way you go, but it's 2.5. Let's see. So the amplitude is 2.5. Okay, so when you're ready, we'll go to the next page. Okay, and we will go to Sarah. Okay, so there's a lot of details, but everybody okay with this idea? Ferris wheel is rotating around in that direction 3 times every minute, 3 revolutions every minute. 5 meters off the ground. It's quite a high Ferris wheel. It's difficult to get on, but once you're there, it's a good view. And the diameter was 20. We'll go to Ernie. Okay, so let's try this. So we'll go ahead and start our sketch. We've got t, or time, down here, and we're trying to model the height. So h for height over here. So we're going to start the clock when the rider is in that pictured position where the rectangle is over there at the far right. So the first question is, how high is the rider at that moment in time? Let's see, so the diameter was 20. So I guess that means that this part right here is 10, and then different 10 up there at the top. And it was 5 meters off the ground, the whole wheel. So initially, how high is the rider? It's at 15. So we'll go ahead and put a 15 right there, and that's where we start. And then the wheel starts to rotate around in the direction with the arrows, and the rider gets higher. And so I guess we'd like to know how high the rider is at the very top. It's 25. We all see that? Originally 5, always 5, and then it's a 10 and another 10. So 25 at the top. So I'll go ahead and mark that as a 25 up here, and I'll put a dot. Now, I don't know, I haven't figured out exactly how long it takes to get there. So, we still have to find that number, how much time it takes. But I'm happy to say that it's up there at 25 at some point. And then let's go ahead and put the rider over here on the far left. How high will the rider be at that moment? It'll be the same 15. It's back at the same height. It's in a different position, but it's the same height. All we want to know is the height. So it's back at 15. I don't know how long that takes. And how about at the bottom? It's only 5. So it feels like the bottom we will ever be is 5. And then let's get back to where we started. How high was that? 15 again. Okay, any question about the 5 dots yet? All right, then I guess the next thing I'd like to do is fill in the question mark. I want to know how long did it take for the rider to get to the top? Can you guys talk to your neighbors? How many seconds does it take for the rider to get from the start to the top? Okay, so I heard some groups talking about the first translation. If it's 3 revolutions every minute, then every 1 revolution is only going to take a third of a minute, 20 seconds. So that's 20 seconds the whole way. In fact, I think that means that 20 is way out there at the far right. That's how long it takes to go up and then all the way back down and then back to the middle, which is where we started. And then how many pieces were there to this trip? Like how many arcs of the circle did we think about? Like this was our first part of the trip, and then that was our second, and then our third, and then our fourth took us home. So this idea of having 4 parts is going to come up a bunch, but this thing right here, I know it's 5 points, but it's really 4 spaces between the points, right? 1, 2, 3, and 4. So how long, if you take 20 and cut it into 4 equal pieces, then how long is each one? It's 5 seconds. So however you do it, should end up with 5 seconds out here. And I guess that makes this one 10 and this one 15 seconds. Okay, and then we'll connect the dots. So I don't know exactly how to connect the dots. It could be straight line to the top, and then straight line to the bottom, and then straight line to the top. That's okay. I have some doubters in the room. Yeah, that's all right. But we're just going to connect them in some way. Maybe you feel like it's connected more smoothly than that. You might think about how the ride would feel. Like forget about the Ferris wheel, but like how would you feel if you were in the cart and it were doing this? How would you feel when you got up to the top? Why would you feel not good? Yeah, we would feel like we were really, really jerked around because we were moving up at a smooth, steady pace, some velocity upwards that was nice, and then all of a sudden, not just stop, but whipped back down instantly. And so maybe you guys are right. So maybe it doesn't quite go as straight as that. but rather like we head up to the top and then we kind of start to slow down. Like it's not a dramatic, instantaneous change at that moment. And then we're gradually going down, and then we go down faster, 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 but then maybe we start to slow down because we know we have to turn around, and so we slow down at the bottom, and then speed up, speed up, speed up. And then I'm pretty sure I've got a good handle of what's going to happen in the next 20 seconds. It's going to be another copy of that thing, right? Like once you're back to the start, then you're just going to repeat the same trip over and over again. So it feels like that's a second copy of the first thing. And we'll go to Vanessa for 14. Okay, so let's try that here. Okay, remember the period is how long horizontally it takes to repeat. And I say how long, I'm not just meaning a distance. Oftentimes it's a time period. How long does it take for this graph to repeat itself? It's 20 seconds. 20 seconds is the period. The midline is the thing that goes right through the vertical middle of the graph. And 15 meters is the middle, right? It's halfway between 5 and 25. It's also exactly where we are when we start our journey in the middle. Midline, I just want to highlight, it's not just a number, it's an equation. It's the equation of a horizontal line. So the midline here is y equals 15. And then the amplitude is how far from the middle to the top. How far is it from the middle to the top? 10. Or how far from the middle to the bottom? 10. It doesn't matter which way you go, amplitude is 10. Any questions on those words? Okay, periodic functions is the group activity. There are two rather lengthy questions, and we have about 15 minutes, so let's see how far we can go. Answers follow.